Notes 4.7 are on rates of change in trigonometric functions. So let's take a look and see what we have going on in our scenario in question number 1. It tells us that Melissa used a motion detector to measure the horizontal distance between her and a child on a swing. She stood in front of the child and recorded the distance, which is represented by d of t, in meters over a period of time t in seconds. The data she collected are given in the following tables and are shown in the graph below. So essentially what's happening is that the child's distance from Melissa started off pretty far, and then it started to decrease. The distance started to decrease, and then she got to a certain point, and then the swing started to move backwards again. And then it was forwards, backwards. So the distance was decreasing, increasing, decreasing, so on and so forth. And she did it over a certain period of time that we have here. So I want to analyze the information that's given to me here. Okay, so first of all, I know that the greatest distance, so the maximum, is going to occur when time is 0 seconds. Okay, the maximum will also occur when time is 0.8 seconds. Sorry, that's a minimum. The maximum will also occur when time is 1.6 seconds, okay? And I know that my minimum will occur when time is at 0.8 seconds, as well as when time is at 2.4 seconds, okay? Now, this information is going to help me to identify what is happening specifically with my rates of change in this problem exactly, okay? So as time goes on, the distance decreases. So between 0 and 0.8 seconds, our distance is decreasing, as well as from 1.6 seconds to 2.4 seconds, our distance is also decreasing. Okay, so our distance is decreasing. But we also know that from 0.8 seconds to 1.6 seconds, as well as from 2.4 seconds to, we can extrapolate and figure out that this would be 3.2 seconds, our distance is increasing. Okay, so based on that, I want to figure out when is the distance, or sorry, we're talking about speed. So here it says, how much did the speed of the child change as the child swung back and forth? Well, we know that speed is equal to distance, change in distance over change in time. But our speed is never going to be a negative value. Okay, so our speed is always going to be positive. So our speed is always going to be the absolute value of our distance over our change in distance over our change in time. Well, this looks like a rate of change to me. So right here, this is going to be our rate of change of our function right here. So how is the speed of the child changing? Well, when I look at my graph right here, the rate of change, remember, is going to be the slope, the instantaneous rate of change, is going to be the slope of the tangent line at any point. Okay, so when I look at this right here, the slope of my tangent line here is 0. The slope of my tangent line here is 0. The slope of my tangent line here is 0, as well as here. So the speed is going to be 0 when, so we'll say speed is 0 when the time is equal to 0 seconds, 0.8 seconds, 1.6 seconds, and 2.4 seconds. Okay, now this should make sense to us because the speed is going to be increasing and decreasing, and then eventually it has to reach a speed of 0 in order for it to be able to turn back around. Okay, so when is the speed increasing? Well, right here, if I look at this right here, if I were to do the slope of my tangent line just a little bit to the left of this 0 right here, my slope is not bad. It's negative, okay, but it's not too steep. But as I get closer and closer down the line right here, my slope is getting steeper and steeper until I reach a time of 0.4 seconds. So when I'm at 0.4 seconds, I probably have my steepest slope right here. Then after 0.4 seconds, sorry, that was not very accurate, but after 0.4 seconds right here, my slope starts to get less and less steep. Okay, so if you look right here, the slope of my tangent line is getting less and less steep that in my graph right here. So again, at 0.8, my slope is 0, and then here my slope ends up being a little bit steeper, 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 steeper until I get to 0.4 seconds. So at 0.4 seconds, this is when my speed is going to be at its max. Okay, so here I can say the speed is increasing between 0 and 0.4 seconds. Okay, then at 0.4 seconds, my speed starts to decrease until I get a slope of 0. Again, my speed is going to be my slope of my tangent line. So then I can say the speed is decreasing along the interval 0.4 until I get to 0.8, where my speed is 0, where I have no speed, okay? Then the child starts to pick up speed again. So the speed is increasing again, starting from 0.8 seconds until when? Until my tangent line is the steepest it can be. So right here, every tangent line I draw here is getting steeper and steeper until I get to about 1.2. So here I've got a maximum speed as well. And then my speed here afterwards starts to level off more and more until I get to a tangent of 0. A slope of a tangent line of 0, okay? So we can see that at 0.4 and at 1.2, those are my maximum slopes right here. My slopes are going to be the largest at those values, the slopes of my tangent lines, okay? And the same is true when I hit right here, 2 seconds right here, okay? So based on that, we can say the speed is increasing from 0.8 until 1.2. Then the speed starts to decrease because it's reaching its maximum right here. So the speed is decreasing from 1.2 until 1.6. Then the speed starts to increase again at 1.6 on the interval 1.6 until it reaches 2.0 seconds, and then the speed is decreasing from 2.0 seconds to 2.4, and then that pattern will continue, okay? Therefore, I can say my answer is the speed is increasing along the intervals right here, 0 to 0.4, as well as 0.8 to 1.2, as well as 2 to 2.4. Okay, and then I can say that it's decreasing, the speed is decreasing. And don't get the distance confused with the speed. The speed itself is decreasing from 0.4 to 0.8, as well as, oh, and I apologize, I have a mistake here. This is incorrect. We would say it's increasing from 1.6 to 2.0. Sorry about that. It's decreasing from 0.4 to 0.8, as well as 1.2 to 1.6, as well as from 2.0 to 2.4. Okay, so now we've used the idea of the fact that it's a slope of a tangent line to help us figure out, well, where is the speed increasing, where is the speed decreasing? Now I want to find my average rate of change. So looking at average rate of change right here, question number 2, it says calculate the child's average speed. So since it's average speed, that's our A rock, over the intervals of time below. So in order to be able to do that, I'm going to figure out my f of 0.8 minus f of 0, okay, all over 0.8 minus 0, because remember our A rock is going to be f of b minus f of a over b minus a. Now, I want to take the absolute value of this answer right here because we're talking about speed, and speed is always going to be positive, okay? So right here, when I look at my chart, I'm going to figure out what f of 0.8 is. So I go to 0.8 and I realize that f of 0.8 is 0.6. So right here, I'm going to plug in 0.6 minus, then I'm going to go to my chart again and figure out what f of 0 is. Well, f of 0 is 3.8. So it'll be 0.6 minus 3.8 over 0.8 minus 0. So I end up getting right here negative, and it's the absolute value right here. So the negative 3.2 over 0.8, take the absolute value of that, I get negative 4. Well, what does this negative right here mean? It means that the distance is decreasing at a rate of 4 meters per second, but my speed is just simply 4 meters per second. It's just going away as opposed to coming closer. Okay, so now to find the average rate right here, I'm going to do the same idea, except I'm going to do f of 1.6 minus f of 0.8 over 1.6 minus 0.8. Take the absolute value of those answers right here. And to figure out these values right here, 1.6 I know is 3.8, has a corresponding value of 3.8. So f of 1.6 is 3.8. And then f of 0.8 we already knew was 0.6. So I'm going to say 3.8 minus 0.6 over 1.6 minus 0.8. Take the absolute value of these answers right here. So I get 2.4 over 0.8. Sorry, I get 3.2 over 0.8. So I get 4. This is telling me, since it's positive, that my distance is increasing. So as the child is getting farther away from us between 0.8 and 1.6, so the distance is decreasing at a rate of 4 meters per second as well. So they have an average speed being the same, even though our graphs look slightly different. That's different than we get to a point where we're trying to find our instantaneous rate of change. So to model the situation of the motion of the child on the swing, Melissa determined that she could use this equation right here, where d of t is the distance from the child to the motion detector in meters, and t is the time in seconds. I want to see if this really makes sense for my equation. So the first thing that we want to notice is the fact that we have 1.6 as our amplitude. So if I look right here, I'm going to look and see, does 1.6 seem to make sense for my amplitude? Actually, let's take a look at the 2.2 first of all. So I know that my axis is going to be 2.2. So when I look at my graph over here, if I go to 2.2 on my graph, sorry, I don't know why it keeps doing that. If I go to 2.2 on my graph, it's very clear that this is definitely my axis. And then it says that my amplitude is 1.6. So if I'm at 2.2 here and this goes down to 0.6, my amplitude definitely seems to be 1.6. So I'm okay with these two values right here, the 1.6 and the 2.2. Now, since it's a cosine function, there's no horizontal shift. It starts at its maximum right here, and it completes a full cycle. And how long does it take for it to complete a full cycle? It completes a full cycle in 1.6. So I know that my period right here is going to be 1.6. So if we know our period is 1.6, and we also know that our period is equal to 2 pi over k, here we know the k value is pi over 0.8. So this means 2 pi divided by pi over 0.8. So I can get 2 pi times, multiply by the reciprocal, you get 0.8 over pi. Well, these pi's cancel out, and 2 times 0.8 is 1.6, which is the period we want. So I totally agree with this equation right here. Okay, so now it says, use this equation to estimate when the child was moving the fastest and what speed the child was moving at this time. Well, we already figured out that the child is moving the fastest at time of 0.4 as well as 1.2. Okay, so, and we can also say that at 2.0 is also a time that they move the fastest. So we know for a fact that time equals 0.4 seconds. She's definitely going at her fastest rate. But how do I find what her actual speed is? Well, to find it, I need the instantaneous rate of change. And to do that, I need to get the delta D over the delta t, and I want the absolute value because we're still talking about speed. So remember, to find I rock, you need to do f of x plus h minus f of x over h. Well, I want my h to be pretty small because my t value is already small. So I'm going to make my h value 0.001. So I'm going to do d of 0.401, okay, and I'm doing d because this is d of t, minus d of 0.4, and that's all going to be divided by 0.001. However, it needs to be in the absolute value right here. So now I'm going to plug this into my calculator, but I need to make sure that my calculator is in radian mode. So I'm going to go to doc, I'm going to go to settings and status, doc, settings and status, and then I'm going to go to document settings, and I need to make sure that my document is in radians. It is, so I'm going to press make default, press OK, and I'm good to go. So I'm going to store 0.401 in as my t value because that's my independent value that we have in our function. And then I'm just going to type this in. So I'm going to type in 1.6 cosine of pi over 0.8 t plus 2.2. So 1.6 times the cosine of, right here in my numerator, I've got pi over 0.8 times t plus 2.2, and I get 2.19372, okay? So this right here is going to be about 2.19372 minus, and then I want to do the same thing for 0.4. So I'm going to take 0.4, I'm going to store it in as t, and then I'm going to copy and paste this, and I get 2.2. And that's going to be all over 0.001. Okay, so now I just need to do my subtraction. So I'm going to subtract these values. So I'm going to take 2.1937 minus 2.2, and I get negative 0.006283 all over 0.001. So I get approximately 6.28 meters per second. Okay, we also know that it's going to reach its fastest rate when time is 0 or 1.2. So we're going to say time equals 1.2. We're going to still use the same h value. We're still going to do IROC is equal to delta d over delta t. Okay, nothing new here. And here instead I'm going to do the absolute value of d of 1.201 minus d of 1.2 all over 0.001. And I'm going to evaluate these numbers right here. So I'm going to store 1.201 in as my t value, and I'm going to copy and paste my function. So we get 2.20628 minus, and then when I do 1.2 and I store that in as t, copy and paste it, I get 2.2 again all over 0.001. So here I get positive 0.006283 when I subtract it over 0.001, and then when I do my division I get about 6.28 meters per second. So that's going to be my fastest rate that I have here. So therefore, I can say right here, therefore, the child's fastest speed is about 6.28 meters per second when the time is equal to 0.4 seconds and 1.2 seconds. Okay, and that's my answer to my question. So hopefully you can see how the instantaneous rate of change is essentially just the slope of our tangent line. Okay, and then hopefully you can see how we can apply IROC as well as AROC to our trigonometric functions. Okay, all right, have a great day.